Good morning, Year 7. So today's lesson is about conservation of energy. So you can pause the video right now and you can write the title in your books. Okay, so the learning outcomes for today are the following. So you need to know the different energy stores. You need to understand the concept of conservation of energy and answer questions. You need to understand what Sankey diagrams are, how to read the information of them, and to be able to answer a few questions with Sankey diagrams. Okay, so don't write anything at this point. Do not write anything. So, as you might remember from last week, you covered the different types of energy stores. So we have chemical energy stored in batteries, fuels. You have kinetic energy stored in anything that is moving, such as a car. You have thermal energy in anything that is warm, such as a heater or maybe a cooker, and gravitational potential energy, which is gained when objects are lifted. So an airplane would have gravitational potential energy because it has been lifted above the ground, and if you were to drop it, it would simply fall down. We also have elastic potential energy. So when objects are being stretched, such as a huge elastic, like that, seen in amusement parks. And we also have nuclear energy, which is energy stored in atoms. So in the sun, we have atoms fusing together, and we have nuclear fusion happening, and a lot of energy is being released. Okay, so the next thing I would like you to do, on your question sheet, which hopefully you have it in front of you, for each one of these objects, can you write down what energy is being used to make them function, to power them, but also what energy is being given out in each case? So you can pause the video right now and you can work on it on your own for about 3 minutes. So you can pause the video now. Okay, so hopefully you finished answering the questions, and right now I'm going to go through the answers, and if you didn't write the answers, can you just make sure you write them down on your question sheet? Okay, so for a cooker, this uses fuel, which is gas, and therefore it is chemical energy. For an iron, it uses electricity, so we call that electrical energy. For a light bulb, it is the same. It uses electricity, so we call that electrical energy. For a stereo, it's electrical energy. Washing machine, electrical energy. And for a man pushing a swing, well, the man uses actually chemical energy from the food. So all of us use chemical energy stored in foods. Okay, and right now for the energy given out for each object. So for a cooker, it uses chemical energy and it gives out heat. So it's thermal energy. For an iron, uses electricity, gives out heat again. So it's thermal energy. Light bulb uses electricity to give out light and heat. For a stereo, it uses electrical energy to give out some sound. For a washing machine, electrical energy to give out kinetic energy. So if you have looked inside a washing machine, you've seen that the clothes are actually moving, spinning around. So anything that is moving is kinetic energy. And the last one, well, the man is using chemical energy from food to actually push and lift the child in the swing. So we have kinetic and gravitational potential energy. So if you haven't done so already, I encourage you to pause the video right now and write these answers in your book, please. Actually, no, on your question sheet, sorry. So write them in your question sheet. Okay, so the next thing I would like you to write down, it is the law of conservation of energy. So this is the title of the lesson. And the law of conservation of energy states that energy cannot be created or destroyed. It can only be transferred from one type of energy into another type of energy. So I would like you to pause the video right now and write this sentence in your books, please. Write this down. Okay, so just like we said with conservation of energy, energy can only be transferred from one type of energy into another. So here we have a skater on a ramp, and if I was to pick up the skater and lift him above the ground, you can see its gravitational potential energy here in blue, it is increasing. As I lift him up, his gravitational potential energy is increasing. And the more I lift him, and this is the maximum, the more gravitational potential energy he has. And if I put him back down, his gravitational potential energy is back to 0. So right now is 0, and right now is maximum. So the higher he is, the more gravitational potential energy is. So what happens if I put him on the ramp? So if I put him on the ramp, obviously he's going to slide down, and his potential energy will decrease. Because if you put something back on the ground, it will decrease as like that. But that energy is not being lost. So I'm actually going to release him and see what happens. So as you can see, all this gravitational potential energy has been converted into kinetic energy, because as he was moving down, he became faster and faster and faster. So remember, something with motion, something that is moving, has kinetic energy. Let's see that again. So, okay, and let's see that again. Right now, he's nearly at the bottom, and his gravitational potential energy is nearly 0, while his kinetic energy is nearly maximum. And again, if I were to put him here, his gravitational potential energy is maximum, and when I will release him, you can see how that energy is being converted into kinetic energy. So this is a really good demonstration. Okay, we can see this in a different scenario, so I'll put him on this ramp. Now, if all the gravitational potential energy would be conserved, as it should be, according to the conservation of energy law, his height should remain the same. So when he climbs back up, he should climb to the same height, and he does. If any energy would be lost, he would eventually go slower and slower and slower, and actually he would stop at some point. But because no energy is being lost whatsoever, he will always climb to the same height. So to the same height and to the same height. But what happens is his potential energy is being converted into kinetic energy, and the other way around. So at the maximum at the top, he has maximum potential energy because he's at the highest above the ground. And at the bottom, he has maximum kinetic energy because he's moving the fastest. Okay, so hopefully that was a nice demonstration, and now you understand that energy cannot be created or destroyed. It's simply converted between one type of energy and another. Here is the case, potential energy is being converted into kinetic energy, and the other way around. So basically, conservation of energy says that energy can be transferred from one type into another. For example, electrical energy can be transferred into light and heat. It is the same with a light bulb. No energy is being lost. Electrical energy, to power the light bulb, is being converted into light energy and heat, because these filaments actually heat up and glow really powerfully. So the next thing I want you to do is to pause the video now and write down this sentence in your books, please. So let's just see an example. So we all know that energy can be transferred from one type into another. So let's see if you can name the type of energy going in and coming out of this TV. So I can actually advise you to pause the video now and just think about it for a second. Okay, so hopefully you have a thought about this. So we know that in a TV we have electrical energy going in, but this TV will give out some light energy, also some sound, because you can hear the sound from the TV, but also it will give out a little bit of heat, and we don't really want that heat. Okay, so the next thing I would like you to do, on your question sheet, you need to complete the flow of charts to show energy being transferred in each situation. So the first one has been already done for you. So here we have electricity going in a radio. So you have electricity and it gives out some sound. That's what the radio does. Now can you do the same for the next two objects? So you can pause the video now for about 2 minutes and have a go at this question. Okay, so hopefully you tried to answer the questions yourself. If you haven't, you can write the answers right now. So here we have a barbecue which uses coals. So coals are a type of fuel, and fuels store chemical energy, and the one given out, it is thermal energy. Now in the case of a TV, so energy needed in a TV is electricity, and the energy given out from a TV, it is light and sound. So if you haven't done so already, can you pause the video now and write down these answers in your question sheet, please? Okay, so the next thing I would like to talk with you about, it is about Sankey diagrams. Now I will spend a few minutes of tomorrow's lesson talking about Sankey diagrams as well, but we need to understand a few concepts about Sankey diagrams today. So Sankey diagrams, they show the amount of energy transferred in a system. Now this system can be a light bulb, it can be a heater, it can be a toaster, a hairdryer, so anything like that. So the first thing I want you to do is to actually pause the video now and write down in your books this sentence. So pause the video now. Okay, so hopefully you finished writing that down. So let's just have a look at these two Sankey diagrams here. So we already said that if we want to make a light bulb work, we need to put some electrical energy in the light bulb. And this electrical energy is being converted into light, but also there's a little bit of heat given off. So the concept of conservation of energy states that energy cannot be created or destroyed. So therefore, the amount of energy going in a system must be equal to the amount of energy going out of the system. So the next thing I would like you to do is to write down this this sentence here at the bottom. So pause the video right now and you need to write down that energy going inside a system must be equal to the energy out of that system. So pause the video now. Write it down in your books. Okay, so in this case, with a light bulb, you have 50 joules of electrical energy going in and 30 joules of light going out. So how many joules do you think we should have here where it says heat? So if 50 joules are going inside the system, but only 30 joules out, how many more joules should we have here? So again, the conservation of energy says that energy going inside the system, which is represented by this arrow, must be equal with the energy going outside of the system, which is represented by these two arrows. So hopefully most of you said that is 20 joules, because 20 plus 30 is 50. So energy going in equals energy coming out. And it is the same in this case. So we have 12 joules of energy going in, but then we have 5 joules of energy going out as light, and also we have 7 joules of energy going out in the shape of heat. So if you add 7 to 5, you can end up with 12. So energy has been conserved. All the energy in has been actually being transferred out. Okay, so the next thing I would like you to understand is how we read information from Sankey diagrams. So this is an example of a Sankey diagram for a light bulb, and which converts 10 joules of electrical energy into 8 joules of light and 2 joules of heat. But we have these terms here, such as total input energy, useful energy, and wasted energy. So we need to be able to understand what these things mean, and we need to be able to read them off a Sankey diagram. So the total energy input is always at the start of the arrow. So the start of the arrow represents the total energy input. So here it says we have 10 joules of energy. And if we look at the thickness of this arrow, so this is the thickness. This is the thickness, how thick this arrow is. You can see it has 10 squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each square represents 1 joule. So 10 joules of energy for that. And if we want to read off the useful energy is always going in the same direction as the input energy. So it just continues on the same path. So this is the useful energy. And the wasted energy is always this one going out. So going down. So you always have an arrow pointing down, and that is the wasted energy. That is energy that we don't use actually, and we don't really want. So one common misconception that I've seen with many pupils is when they try to read off the energy from a Sankey diagram, they're actually reading off the length of the arrow. So they are reading it out like that. This is the length. Now you don't do that, you always read the thickness. So this is the thickness, this is the thickness again, and this is the thickness of the arrow. So I really want you to pause the video now and to write this sentence in your books, that the width of the arrows in a Sankey diagram represents the amount of energy in joules. So pause the video right now. Okay, so hopefully you finished writing all these things down, and now I will give you an example. So here we have a Sankey diagram for a stove, and it says that the energy going in, it is 100 joules from coal. The energy that heats up the room, which is useful energy, is 75 joules, and there is a certain amount of energy escaping through the chimney. So using the conservation of energy, have a think and guess how much is this energy escaping out through the chimney. How much do you think it is? If you have 100 joules going in but only 75 coming out, what value would you give here? Is it 75, is it 25, or is it 100 joules? So you can actually pause the video now and work out this question. Okay, so hopefully you had a go at answering this question. And so again, if we say that all the energy going inside a system must be equal to the energy going outside of a system, we have 100 joules of energy going in, but only 75 joules going out. Well, then this energy should be 25 joules, because 25 plus 75 is equal to 100. So hopefully that's the answer you got. And if you didn't, just make sure you write this answer in your question sheet. You have this question in a question sheet, so just make sure you write it down. Okay, and the last thing I really want to talk with you about is about efficiency. So a device with higher efficiency will transfer more energy in the useful energy. For example, a light bulb transferring electrical energy. So I really want you to pause this video and write this sentence down in your books, please. So make sure you pause the video and write this sentence down. Okay, so, and really all you need to understand is that some electrical appliances are more efficient than others. So for example, let's have a look on the slide. Now here we have some incandescent lights. So these are the old type of light bulbs. We used to find them in every household, and right now most people have been switching to more efficient ones. So this bar here, it shows you how much energy they use per the amount of light given. So for the same amount of light, you can see how incandescent lights, they use about 100 watts. So that is a lot of energy. Now then we have other light bulbs with halogen light bulbs, and this bar is smaller, so they give out the same light, but significantly less energy is required for that. And then we have other halogen light bulbs which use even less energy. Then we have fluorescent light bulbs which use only 20 watts for the same amount of light, only 20 watts. So that is an 80% decrease in the energy requirement. Then we have fluorescent tubes which use about 18 watts. And then we have LEDs, which at the moment they are some of the most efficient light bulbs we can find. So most people these days have switched to LEDs, simply because for the same amount of light given, they use so much less energy, so they are more efficient. So you can see how these ones were very inefficient, but LEDs were very, very efficient. They use about 18 watts of energy. Okay, so that was really everything I wanted to cover with you today. So thank you very much for listening, and I hope you're going to have a nice rest of the day. So thank you.